Okay, good morning, everybody. Starting a little late. My name is Sriram Ramaswamy, and I'm chair for this session. First speaker is Mustansir Barma, who will talk about this.
Thanks, Sriram. Organizers, thank you for the invitation, and it's a great meeting, and really enjoying being here. Okay, so today I'm going to talk about this thing, about formation of condensates in the Takayasu model. And I'll define terms as we go on, but basically these are models of aggregation. So aggregation in the model sense will mean the following, that you have particles which are moving around somehow, maybe they're diffusing random walks or something, but when they come close and jump onto each other, they stick. And then having stuck, they move around together, and so on and so forth. Of course, it might happen that something breaks. So you have a lot of mass on one side, it could break. But the breaking rules will allow are not, usually considered are not that you break it in the middle, but maybe one mass can chip off or something like that. Anyway, that's the general scenario. Moreover, and this is important, you can have input. It may be raining. So you can have one mass added on every step. And so you could either have models with conservation, with no rain, strict conservation law, or models with no conservation and sort of violently no conservation because it's coming in all the time. So this is the... there could be, and I'll refer to it a little bit, it won't matter in the context that, in some contexts, but in the model that I'm going to talk about, there isn't. All right, so, okay, so this work was done with a bunch of postdocs and students at TIFR Hyderabad. Argodas is now at Math Science. Chandrasekhar Iyer was around one day here. He is on his way to Rome, if bureaucracy allows. And Rhea Negi is from the University of Hyderabad, and she spent a year with us. And she's on her way to France, if bureaucracy allows. I think it has allowed. And Rajiv Pereira is a postdoc continuing at TIFR Hyderabad. Okay, so support from various agencies, and let me move on. So this is the sort of scenario I was talking about. So consider mass space. Okay, so the aggregation move takes a mass m1, there's an m2, and maybe they will join up. So in mass space, suddenly there's a big increase from m1 and m2 to m1 plus m2. That's the bent arrow that I've drawn here. So there's a mass which is increasing all the time. So aggregation would promote motion upward. But then, either through this chipping or through this input rainfall, there's also replenishment at the low mass end, because what is coming in is small masses, mass 1. And so you can imagine a steady state setting up in this mass space. Okay. All right, let me talk for a short while about the conserved mass model, where there is no rainfall, nothing. There is some breaking, but this is the model. So there are two models we actually looked at. One is a very well-known model in statistical physics. It's called the zero-range process, first introduced by Spitzer in the 1970s, I think. But there's a very nice review by Evans and Haney here. And what happens in the zero-range process, as a result of aggregation, you have an uneven distribution of masses, and looks like that. And once in a while, something can chip off, namely one particle can fall off, but if it falls, it will combine with another mass if there is one next to it. All right. The whole stack can also move. No, sorry, this is zero range. There's no movement. This is the only move, only chipping. But the chipping rate, importantly, depends on the amount of mass on the site. So for instance, U of 2, because there are two sites there, two masses there, will be different from U of 10 and so on. Now, in this, first of all, this model can be solved exactly in the sense that one knows the steady state exactly. It's a product measure state, as pointed out, in fact, by Spitzer when he defined the model. But when the chipping rates have a particular form, which I've written here, and for a particular range of parameters B, there's an interesting thing that happens. And that is a condensate forms. Now, what do I mean by condensate in this context? It just means that there's a single site which holds a finite fraction of all the mass. It reminds you of Bose-Einstein condensate, but this is, of course, in real space, not momentum space. So where is that site? That you can't say. There's a spontaneous breaking of some symmetry, and it'll form somewhere. If your system is finite and you wait very, very, very long, it'll form somewhere else also. But for a long time, basically, if your system is very large, it'll just stay put in this model. There's another model where these conglomerates are much more dynamic. It's called the conserved mass aggregation model. And it formed, I think, part of Supriya Krishnamurthy's thesis. There she is, right? And what happens here is that not only do you have breaking, which is independent of the mass on the site, but also you have diffusion of this whole guy. So this moves here and can get bigger. Okay, so these are the two models. This also shows very similar broad behavior. There are differences of detail, of course. And the condensate I emphasize in both cases is a finite fraction of the total mass. So it reminds you of Bose condensation. So let's look at the sort of things that happen. So what happens in these models is actually a phase transition as a function of density. Remember, total number of particles is conserved, but okay, I have a certain density, but treating that as a control parameter, I can ask what happens, and the answer is that if you look at the probability that a certain site has mass m, call it P of m, and you plot that versus m, well, that's an exponential fall in the so-called normal phase, which is rho less than rho c. As you increase rho, there's a particular critical value, rho c, at which this slowly becomes a power law. Okay, and of course, this is cut off in a finite system, but it's a power law. But the interesting thing is what happens when you go beyond. This power law does not change. When I say does not change, I don't mean the power does not change, but the distribution doesn't change. It stays put. Okay? But then what happens to the extra mass since you've crossed rho c? Well, it piles up in the condensate. Anything extra is there. So that's the phenomenon. This is what we call condensation. And it's sort of interesting to ask questions about it. The question we were interested in, if I can get this to move, is the following. What I've described to you is what happens in steady state. The question is, how is steady state reached? Okay, that's the question we asked. Okay, and the answer is roughly the following, that you start with a disordered state, mass statistically uniform, and you ask what will happen. Let some time pass. So what will happen? It stands to reason that masses will move around, of course, but diffusion will limit the amount of distance they can move in a time t. So in a time t, they'll move order square root of t distance, and therefore there'll be some rearrangement of mass on that length scale. And this is what you see, in fact, when you do a simple simulation. But remember what that rearrangement will do. So you have this root t, L of t, sometimes they call it, distance. So there must be a condensate that forms there. But it will be of size roughly L of t. It can't be the system size, because the system has not been probed. So indeed, this is what happens. So you form a lot of small condensates at a certain time. As time passes, fewer condensates, but bigger ones, and so on and so forth. Right? So, okay. So what we investigated is, the properties of this, the distributions of condensates as, as this coarsening, if I can call it that, proceeds. Okay, and the answer is something like this. So here are the distributions at different times. Time is moving rightward. And you can see that there's a distribution with a bump. And that bump is the condensate. Okay. Now, you can do a simple scaling, and you get a nice bump collapse over there. But if you've collapsed into a single scaling function, it means, first of all, that m star is proportional to L of t, but also the standard deviation is proportional to L, because it's a single function. So it's very fluctuating. That is all right, but steady state, we know that the standard deviation does not grow like system size. It grows like system size to the somewhat lower power, 0.7. So, in time, in a finite system, L of t will reach the system size. So what happens? So we asked that and we answered that, but I won't tell you too much. Well, basically what happens is that something of order L, of course, is much bigger than L. So this approach is very strongly non-monotonic. It goes up and then comes down and settles to steady state. And we understand features of this, why this happens, what happens, and all that. But this is still the conserved mass model. So I want to now go to the non-conserved one, because that's sort of, even in our view, even more interesting. So let me just tell you about that. Yeah.
So in the condensate phase, there is only one?
There's only one peak in steady state. On the way to steady state, of course, there are many peaks, but in the steady state, there's only one. Right. Okay. So let me introduce you to the Takayasu model. This Takayasu is from Japan, and his papers sort of reflect that. He'll always talk about Japanese gardens and pebbles and water. It's very nice, right? And the model is actually a central model. So it's central because it has connections to many, many other important models of statistical physics. Okay, so I'll tell you a little bit about that. In fact, as I'll make clear, Takayasu is not the first to come up with the model. This model, there's a person named Scheidegger, we'll talk about him in a while, who actually came up with this model. But Takayasu and company, I'm emphasizing and company, were the first to solve major aspects of this model. Okay. Right. So what is the model? The model is very simple. It's exactly what I said. These clusters move around, they combine, combined cluster moves, no chipping. They just keep growing. Total mass keeps increasing. Because there's rainfall, because there's one particle coming in per site per unit time. Okay, so the clusters move like that red one here, and if it moves, it will combine, and so on and so forth. So it's just diffusion and coalescence plus injection, as minimal as you can get, and fine. Now, what is the interest in this model? The first and most striking thing is that this is perhaps the simplest model of self-organized criticality. You're not doing anything, you're letting things move, they do, they go, and you get a power law immediately. Immediately means after 50 Monte Carlo steps. So, you don't have to wait very long. You just see it. It's a very robust thing. Yeah, okay. And
Injection rate is
1.
1, meaning 1 per time step.
1 per time step on each site.
On each side.
Every site, yeah. So it's really raining. Yeah. Yeah. And here's the answer. It's an analytically derived answer for the power law. P of m grows like m to the minus 4 by 3, which you will realize is a slow power law, but it's a power law. You can also look at 2-point correlation functions in this model, and I think Rajesh and Satya looked at those, and you find interesting behavior there also, but I mean, this is what it is. Okay, so now I'm going to tell you that Takayasu and Huber and everybody knew what is going on, but not completely. So let me tell you what they missed. Okay, now the first question you may ask is, will this model ever reach a steady state? Because the mass is increasing all the time. So of course, if you ask for total mass, that will increase, actually totally linearly in time. But something might reach a limiting form, and that something is P of M. For instance, I mean, it might happen, and that P of M decays as a power law, like here, but it's cut off at a certain time because there's, only so much mass has come in. And the way this could reach a limiting form is that you keep increasing the time, and you see more of it and more of it and more of it as time passes. So, okay, it's also easy to see that the largest mass will scale like T to the 3/2, okay? Simply from the sorts of arguments I gave earlier, so L of t is the distance over which things have gathered up. It's proportional to root t, but the amount of mass that has fallen in is proportional to t, to that length. And so the 3/2 will work out immediately. Okay, so here is what the world lines of the Takayasu model look like. This is from Takayasu's paper. You can see a certain care in the figure, nicely done. Right. So what we're looking at is a space-time diagram. So this is space running horizontally and time. And you can see this sort of intricate pattern of things coming together, coalescing, et cetera, and this is very nice as world lines, but it immediately reminds you, or may remind you, of rivers. After all, rivers are made of tributaries. Tributaries are made of sub-tributaries, and they all start at some mountaintop, and something happens, and that is what the top line is, a mountaintop. And then things are combining and coming down. So this is a model that was considered earlier on by Scheidegger, much earlier. Scheidegger was interested in the size of river basins. Now, river basin is not a delta. Everybody thinks of delta and, something, okay, delta. But we are thinking of basin. What is a basin? A basin is the area from which something has come up to that point. So there could be many basins, because different things feed into the river. And you ask for the distribution of basins. Now, Scheidegger looked at a particular valley in France where there were many small rivers and so on. And he probably looked at other things also, and he found that the area of these basins follow a simple law. It's simply area to the minus 4/3 for the occurrence of these. And from this picture, it's immediately apparent that the mass somewhere is actually proportional to the number of sites that fed in here, which is indeed the area. So this Takayasu aggregation model gives a very nice explanation of this a to the minus 4/3. In fact, Scheidegger had defined the model, but he did not know how to solve it analytically. But I think he did simulations and found that this is actually working. Now, this is one important application of the Takayasu model, but then there are others. If you time reverse this, it becomes the voter model that we heard about from Parangama. And there's another nice analogy. If you think about granular stacks, where things are stacked, but they're not, the force is not transmitted vertically down. I mean, it depends on contacts and so on. So if you think of transmission of the force in this way, you quickly land up with exactly Takayasu type arrangement. So Coppersmith et al., and the et al. Includes Satya, looked at this analogy and used it. Okay. And there are other analogies, importantly also to the directed sand pile model. I mean, there's a connection between Takayasu and that. So Takayasu is an important model, but now, how did they solve it? I'll just indicate what they did. Is this true? Oh. Okay, so I speed up enormously. All right, we won't go into details. There's an exact recursion you can write for the amount of mass in a bunch of R sites. You can write a continued fraction from that recursion. You can solve it, and you find this P of m going like m to the minus 4/3. Very beautiful derivation, largely due to Huber. But something is assumed in this. And what is assumed is that you've taken the limit time going to infinity already. It's important. I mean, you're not approaching the steady state by looking at a finite time and then another time. And if you take the limit time going to infinity, this is what you get. But we did a simulation and we found this. At a certain time, the answer is not just a power law, it's a power law with a bump. As time passes, the bump progresses. Simple scaling by t to the 3/2 actually produces a scaling function with a bump. The bump actually signifies a condensate. There is a condensate in this model. The source of the condensate is not conservation, because nothing is conserved, but it is there, and you can see it immediately in simulations. Now, this was missed because of the way the limit was taken. Okay. It's not a trifling condensate. It holds 80% of the mass, okay, on average. So what we decided to do is that since we have exact recursions, let us just see what they give. And they give you, indeed, a power law with a bump. Okay, this is some Fourier transforms and so on. And this continues, but in a finite system, eventually you will reach a steady state. And the steady state actually has a single condensate. So, this is on the way to steady state, and this is in steady state. It's a single peak. Whoops, okay. I'm moving on. One can understand the occurrence of this condensate in this system through a simple observation on how random numbers, which are distributed as x to the 1 plus alpha with a small alpha, are distributed. The ratio of the sum of n such random variables to the maximum on average is a finite number. Result due to Darling, and it's there in Feller. So this sort of justifies it. Of course, these are independent. But now, let's turn to the condensate, if I can, in the next 2 minutes. See, the condensate is a mobile condensate. It's moving around. Wherever the condensate is, you expect a depletion of mass around it, because it has sort of swallowed up the mass. So how to find out, is it there or not? The best thing is move with the condensate. So at every instant, we just move origin to the condensate, wherever it is, and look around. When you look around, you find an extremely simple distribution. Here it is. The mean mass, mu, at a distance r from the condensate just looks like this. You can actually derive the analytic form, x into 1 minus x something. The standard deviation looks like that, but it has a square root here rather than linear. But notice my axis is r by L. So this condensate has a macroscopic effect. Not only that, but how can you ever get distributions like this? What power law will give you that? So it's simple to work out. The answer is 5/3, not 4/3. So just this observation leads you to think that you should have P of m going like m to the minus 5/3, at least close to the condensate. So do you? So you just do a simple simulation. You see very distinct yellow 5/3. This is the site next to the condensate. It does decay as m to the minus 4. And there is the average of all sites is 4/3. Okay, then you can investigate crossovers and things like that. May take one more minute.
Yeah.
Thank
So
you.
you're stealing from your question, kind of.
Oh. Okay. All right. Okay. Fine. All right. So this in some sense is our main point. First, that there is a condensate. Second, it has a huge implication on the landscape, provided, but to see it, you have to move with the condensate. Okay. Last slide tells you something that's sort of obvious. If you have a finite system and you have a condensate and it's diffusing, it may fall off because it's finite, open boundary conditions, not periodic. If it falls off, the mass will come crashing down. And that's what you see in these pictures. The mass goes down, then slowly builds up, down. This is intermittency. So you can characterize it by standard measures of intermittency, which involve moments and so on. You remember something from Rahul Pandit's talk. And indeed, there's a very clean signal of intermittency, strongly intermittent. And we'll leave out 2D, and we'll come to the conclusions. Condensates are there. They reconfigure the mass profile. There's a new power law in the Takayasu model with macroscopic consequences, m to the minus 5/3, in addition to 4/3. It will have implications for these connected models, but we have not worked those out. And we think there ought to be condensates in other models, like the in-out model, which includes evaporation. Thank you.
The POM, the bump in the POM, and how does it compare to other condensate profiles that Satya, Martin, and others have found?
Okay, we have not computed it analytically, certainly. No, and we have actually, we know numerically very well what it is, but we have not compared.
Do you, the shape that it has, does it retain at some point some time dependent? Is it always time dependent, or does it reach a kind of steady state? I understand that it moves to the right, but right. The shape itself?
The shape is preserved. It scales perfectly while it's moving. Eventually, you reach system size, you form only one condensate. All the extra mass that comes in through the rain eventually goes into the condensate. The rest of the system actually reaches a true steady state if you subtract the condensate. Now, that condensate also has a width. But, okay, not having done it, I can't say for sure, but it will be broader, I think, than here, because there are bigger fluctuations in the Takayasu model.
Does it broaden with time? I'm not
sure. Yeah. Right. Yeah, let me stop at that. That is true. Okay, actually, we have not done it. Thank you.
I have another question, Mustansir. This 5/3 exponent, you also find this charge aggregation model, right? So is there any sort of connection between the two?
Yeah. No, so this question was asked to me earlier, in fact, by Satya, somewhere else. And, the first answer is that in an obvious way, there is none. However, realizing that this is a macroscopic consequence, it means P of m is m to the minus 4/3 plus corrections, which include m to the minus 5/3. So in principle, it should be there in the recursions. So we tried to analyze, through the injection kernel and so on. But then things don't work out neatly. But you can see indeed that the next term, so there's an average I meaning the injection. Next term is average I squared. And that is your chart, because I squared doesn't care about, so that would induce a 5/3, and I believe that mathematically that is indeed the mechanism that will do it, but we're not able to show it.
So, I mean, your model naturally generalizes to higher dimensions. I mean, is that something which you looked at, or set of interest?
Yeah, so if Chair will allow, I will reverse. So this is what happens in 2 dimensions through simulations. And indeed, there is a bump, but it is much milder. Now, also, we are not sure what happens as we increase the size, whether the condensate stays or goes away. So at the moment, we cannot say. But given that random walks sort of always come back, even in 2 dimensions, maybe it will stay, but be mild. I'm not sure. But it's a very interesting question and something we would like to answer, but we don't have an answer.
Two. So one is in the CMM model. There also, if you sit on top of the aggregate, depletion nearby.
Yeah.
So is there a power law different from 5?
Yeah, so we investigated that, and I think that there was a question asked earlier to me by Supriya on exactly this point. And we investigated it. It doesn't seem to have a very macroscopic effect. There is certainly a depletion, but remember, in the CMEM, the power is 2.5. So it's a rapid decay compared to 4/3. Whenever anything decays with the power smaller than 2, there's a good reason to expect a condensate through the Darling-Feller argument.
Okay. I think we postpone further discussion.
Okay.
And thank you.
Thank you.